Alright, so in this video we'll begin section 13.1, which is functions of several variables. So we're just going to start by orienting ourselves with the more familiar R2 and then switching to R3. So R2 being 2 dimensions, R3 is 3 dimensions. So if you see me, I try to avoid using that terminology, but I forget a lot and sometimes I put it on homework or assignments. So I apologize if I say R2 or R3. Just keep in mind R2 is 2 dimensions and R3 is 3 dimensions. For a function of one variable, y equals f of x, which can be read y is a function of x each single input or variable x has an output y equals f of x, which we represent visually as, so we would just have this in 2 dimensions. So we have some x, some y, and then we have the point x comma, this is f of x, our y is f of x, or rather x comma y. So that's how we represent that for a function of one variable. So now you'll notice the function of one variable is in 2D or 2 dimensions. So now if we switch gears for a function of 2 variables, z equals f of xy, which can be read z is a function of x and y. Function of x and y. The input or the pair x comma y is a point in the xy plane. So our inputs are things like this. For our function of 3 variables, we would take some input in 2 dimensions or in the xy plane, and the output z equals f of xy is a point directly above slash below, directly above slash below xy in 3D or in 3 dimensions. So 2 dimensions, we put in an x, and there's a y that's directly above or below it that it corresponds to. Now our inputs are anything in this plane, and then it's going to give us an output that comes. So if that's our input for our function z equals f of x, y, the output could be, say, up here, or directly below that point. So now we sketch in 3 dimensions. Actually, I'm going to go to the next page so there's a bit more space. So now looking at 3 dimensions, we sketch our set of coordinate axes. So my input will be some point in the xy plane. So that point right there. So that's x comma y. Our output would be some point here, which is x comma y. So we take that and then those, and then we take f of x and y. But we normally would just represent this as x, y, z. This is x comma y comma z. And so our input is something in the plane. Our output is going to be just something that's directly above or below that. So that's a function of 2 variables. So the input of a function of 3 variables f of x comma y comma z is a point x, y, z in 3D. Thus, its output f of x, y, z is in 4D and cannot be represented visually. So for us, we'll be considering things just up to 3 dimensions, but I just wanted to mention a function, or things just variable functions of 2 variables, I just wanted to mention functions of 3 variables and beyond, just so that we're not thinking that what we're doing or all these things are restricted to functions of 2 variables. We can do things with functions of 3 variables, we just can't visualize them. I mean, and you all know things that are functions of 3 variables. So say, for instance, we define the function being how well you did on your test. And yeah, that could be a function of how much sleep you got, how long you studied, how many suggested problems you did. So that's 3 variables right there. And the list could go on is, did you eat your breakfast that morning? You can define functions of any number of variables, and it's not necessarily something that you can visualize, and it's still a function just as well. So we don't need the visual component for something to be a function, although we use it as a tool quite often. All right, so now there's a definition that we'll need. So the domain of a function of several variables. So our section is titled functions of several variables, but again, we'll probably and we won't at all go beyond 2 variables, even though these things still apply. So the domain of a function of several variables is the set of all points for which the function is defined. We represent the domain of a function, the domain of a function f by DOM of f, or would you say the domain of f? All right, so let's look at an example. In your textbook, we will look at number 2 on page 823. So page 823, number 2. And the directions there say, in exercises 1 through 12, find the domain of the function. And they give us that our function is f of xy equals the square root of x plus y. So from our knowledge of the square root function, we know that whatever we're taking the square root of has to be greater than or equal to 0. So that tells us x plus y has to be greater than or equal to 0. And that's sufficient if you wanted to write y is greater than or equal to negative x. That's fine. On occasion, you might need to sketch your domain, but this problem doesn't ask us to sketch them. So either one of those is sufficient. Now, you're going to see this notation in here quite regularly. So I'm going to go ahead and introduce it early on. So the way we would write this, because we can't do like in previous courses, we could write our domain in terms of an interval, but we can't do that in here. So you all may have seen this in some other courses. Domain of f equals the set of points x, y. So this is just a curly bracket, and then such that, so you just put a vertical line right there. And then you put x plus y is greater than or equal to 0, or y is greater than or equal to negative x. It doesn't matter which way you write that. So x plus y is greater than or equal to 0. And then you close a little curly bracket. So it's just saying the domain of f is a set of points x, y. And this behind this vertical line is the rule that those points have to follow. It says set of points x, y such that x plus y is greater than or equal to 0. So I want to introduce that early on because you'll see it in this section, and then you'll see it in subsequent sections as well. All right, so let's do one more of those. We'll look at number 6 with the same directions, and they give us that g of xy equals the square root of 25 minus x squared minus y squared. So again, we'll use our knowledge of square root, which tells us that 25 minus x squared minus y squared has to be greater than or equal to 0. Now, oftentimes, especially later in the course, we'll want to kind of see what does our domain look like versus just writing down what is our domain. So let's rewrite this as x squared plus y squared is less than or equal to 25. And I'll go ahead and sketch this one since I just mentioned it. So this, and we're just sketching our domain. We're not sketching this function. We're sketching the domain of the function. So those sketches look very different. So the domain is a set of points. So remember, your domain is in the XY plane. We're not sketching a function, so we're not sketching this thing in 3 dimensions. Or if this had an equal sign right there, which that wouldn't be our domain. That wouldn't be the domain in this scenario. But if it had an equal sign right there, it still would just be something in the plane because it's the domain. It's not some function 3 variables. So you have to be careful and keep in mind what it is you're considering. Are you considering the domain or a function? So here, this domain would be, that thing is called a closed disk. And now, if we were sketching the function, then we would plug numbers in that were inside of this closed disk or in the boundary of that closed disk, and that would give us a value that's up above here, below here. Now in this scenario, it's going to always be something above here because we have the square root. So we will get some picture that's up above this thing. All right, now if we want to just write out what our domain is, the domain of G equals the set of points x, y, such that x squared plus y squared is less than or equal to 25. All right, so we'll stop this video here and then we'll continue, and I'll talk about the graph of a function, and we'll start sketching some 3-dimensional things in our next video.